Hi everybody, I am Gabriella Tarantino, and today I'm going to present our work, which is on a different kind of metamaterials, basic cellular metamaterials, which contain a random pore feature. And strictly speaking, I'm going to go through their computer design, their laser powder bed fusion additive manufacturing, and finally I will jump to experiments and some conclusions. First of all, what is that makes a random material, porous material, a bit special? They contain non-periodic architecture, of course, and they can be used in many different applications, which span from functional application like energy electrode to biomimetism without considering the main structural application or load bearing application for this material from transport to health. Now this talk will deal in particular with the current chapter of this research axis, which we started several years ago, and which is about different types of random metamaterials, which span from polymer-based to metallic-based metamaterials, and which is the current objective of this talk. Now, let me first tell you how we make them and why they are interested from the point of view of science. I'm just taking an example of comparison of random metamaterials with periodic metamaterials, which are widely used and known, in particular the octet rust lapides. And I'm going to show just a few results of our early work on this subject. In particular, we can see that the design of this material lies on a very solid theoretical base, and in particular this material, which contains particular type of porous inclusion, can be considered like the first experimental realization of the well-known composite sphere assemblage model. And by this nature, they can be seen to have relative elastic stiffness, which is by far stiffer than conventional metallic bonds produced by standard metallurgical process, and they can rival also periodic octet rust lapides. But this is just one example of comparison which we have bumped into. Now, the tricky part of this of the random metamaterial is how to design them numerically. Because like all metamaterials, they have first to be designed, and then their STL model is generally given to the 3D printing for fabrication. We use a random sequential absorption algorithm, which is a very versatile algorithm, and which we have developed over the years. Basically, its working principle is pretty straightforward. It consists in placing random inclusions in an arbitrary matter, so they are heterogeneously dispersed in a solid volume. What is the advantage of this method is that we can control the particle shape, the particle size, and eventually the orientation. So basically, we can have a very large palette of microstructure, which span from isotropic to anisotropic. Now you have seen that this is I presented the general algorithm for the 3D version of this metamaterial, but when it comes to metallic 3D printing, our material contains closed pores. And that's essentially a challenge when we go to the laser powder bed fusion fabrication. So essentially, the stock will be with the 2D version of this material, which allow the fabrication by metallic additive manufacturing. Our material don't contain pores, which are true thickness and are essentially designed with the same algorithm in the 2D version. Now, when it comes to metallic 3D printing, and that I can say by experience, unlike the polymer 3D printing, we have a wealth of process parameters which we must take into account. Now, the former are, well, parameters are the conventional parameters which we all know in laser powder bed fusion additive manufacturing, basically how we constructed the volume. But the peculiarity of this material is that they contain particles which are embedded into the matrix. And as you can see from the sketch here, most of the majority of the volume of this part is built using the contour parameters. A basic lexicon before I walk you into the results of this work is that we have to consider parameters which imply, for example, other vector definition, like the border, and how we make the junction between the volume and the border, which is in the lexicon it's known as lexicon. You can see that the impact from this basic sketch, that the impact of this parameter is actually pretty huge. And to be honest with you, we were not aware of how much these parameters are really relevant in the proper fabrication of this microstructure. So when we change the distance, the contour parameter, the actual mode and the actual result on the 3D printed part is pretty different. And to optimize this parameter and to analyze them via topological analysis, we really run a large experimental campaign taking one single numerical model which feature on average 20% pore and contain about 200 pores, and we scan all these possible combination of the parameter. Now, to make a short story long, I'm gonna just go to the main result of the experimental campaign before presenting a summary of the results. Now, if we change, taking the same numerical model, if we just change what we call the beam offset, basically the distance between the contour parameter and the STL outer edge, we can see that the same numerical printing model can be printed with huge differences. And we quantify those differences via image post-processing. We can see, first of all, that mono-size pores cannot be printed. Essentially, the microstructure contain pores which are polydispersed in size. They are essential, they resemble a perfect circle, but in reality they have an elliptical shape with the aspect ratio diminishing with increasing the distance, this parameter, the beam offset, but they remain of pretty good round shape. Now, the visual result is clear. Of course, it has a strong impact on the porosity, final porosity, which can appear to be very different from the target porosity. And then we quantify as I said, a campaign where we vary many other parameters like the fill and also the order by which the structure are 3D printed. We can see that porosity can vary by up to 70%. And that, of course, make us think that there is a huge impact of this process parameter on the resulting mechanical properties, which we try to quantify next. What I'm going to present you there is just a summary of the results, where we estimated the elastic stiffness. A part of our work currently also concerns the elastoplastic damage of this material. Now, if we have to measure this 3D printed model, we used standard compression testing, and basically since our post-treatment has revealed that the material also contains a negligible percentage of defect, we carried out a uni-action quasi-static compression test with several steps of loading and unloading the cycle, and we estimated the measured elastic property from the unloading step. That's pretty standard, but in order to follow our strategy, which goes from the design to the fabrication and to the experiment, we needed stable predictive model for this material. And for this reason, we developed an image-based finite element protocol, which allows us to transfer the experimental micrography into image-based finite element model. I'm going to spare you the details, of course, of this process, but the reason for that is that we have seen that the numerical model is not sufficient by any means exhaustive or representative of the real microstructure. And so, as a summary, before just jumping to the conclusion, we could see the comparison between the experiment, this simulation, which we carried out in linear elasticity and using Pareto boundary condition, are pretty good. And one striking feature of this material, that this material still preserved in the 2D, is that they approach the Aschen-Strickman bound, which are known to be the tightest possible bound for isotropic porous media. In the end, I want to summarize the main result of this work. So essentially, we transfer the method we have developed for the generation of random porous material to metallic cellular materials produced by laser powder bed diffusion additive manufacturing. We have seen that the manufacturing of complex porous architecture is tricky with this process, and we have to account for a breadth of parameters which is generally neglected in other simpler microstructure. And finally, the comparison between the experiment and the simulation is pretty satisfactory. I want to just open a perspective, which is where we are going next, and why we spent such time in optimizing the way these materials are fabricated. Because engineering the porous architecture is pretty demanding for application where we need the precise design of the pore feature. Our major target application is to switch to functional application like electrode architecture for high capacity electrochemical energy storage device. And with that, I thank for your attention, and I'm open to any questions.
Thank you, Gabriella, for the inspiring talk. The paper is open for questions. Yeah.
One question. Why do you consider, like for the specific case of the lithium-ion battery, you would like that the transport is homogeneous across the cross-section of the structure? Why would you have then porous architectures, like random porous architectures? Wouldn't then be the transport also heterogeneous?
I very much thank you for such a question. There are actually two tricky considerations. One is purely related to the structural integrity. And basically, this material, since they are pretty safe mechanically, we know that the lithium, and especially they contain silicon. So silicon is known to expand by 300% in volume. We know that they require robust electrode architecture mechanically. And so for this reason, the random architecture are known to be highly damage resilient. That's the reason why we moved to random architecture. And you mentioned a second point, which was related to also to the way that perhaps I can add a complement. Since we have pores and lithium pores which are through thickness, it's essentially that's our electrochemical colleague drove this conclusion. It is possible that since the lithium is prone to make dendrites, it is possible that they alter the transport properties by adding disorder when compared to the periodic architecture which have been currently explored.
Thank you. Very interesting.
Any other question? I have a question, Gabriella. Do you expect the need of any post-processing for any of the applications you have mentioned? I mean, you have up to, or you can expect up to 80% porosity. This is also a huge amount of area available for uncontrolled post-processing and so on. Do you have any experience with that?
To answer your question, I have to, which goes directly to the point. Now, I have to just to say that switching or moving to the metallic actually made our expectation a bit more realistic and less ideal or naive, because we have actually seen that moving to, because of the resolution of the process, porosity, which we are able to attain with the 3D printing polymer technology, are unattainable by the metallic process. Now, coming to the post-processing, I suspect that yes, in a sense, so far we did not use any post-treatment, for example, to correct the roughness, but it could be an option when we will move to the real functional application.
Okay, thank you so much.